Today we'll start with a new topic, three-phase induction motor. We have learned about your three-phase system. Now we'll use that three-phase system as a supply. Okay. So that three-phase supply will drive a induction motor now. So motor principle, you know how it works. We'll learn about that little bit. Again, it is another very easy topic. So very few selective topics are here. So three-phase induction motor is another very easy topic for you to study. Very small topic also, like three-phase system. So three-phase induction motor. So from its name, we can understand it is a motor and it is being supplied from three-phase. Now, by now, you may have understood that in a motor, there are two parts. One is your static part, one is your rotating part. If you consider a DC motor, that static part was called your field, that is your magnet, which was producing the flux. And that rotating part was called your armature, which was rotating. And that means it consists of conductors over there. Same over here. We'll consider, we'll just name that differently over here. We'll have a stationary part, which is known as the stator. From stationary, stator is coming, and the rotating part is called as a rotor. So from that rotating part, rotating term comes the rotor term. So it is similar as your field. So field is similar to your stator, and your armature is similar to your rotor. Only different names are used. So we'll just go by what are the base. Have a small introduction today and try to understand the constructions of induction motor for today's class, and a bit into your working principle. So first point, let's go point wise so that you can understand it very nicely. A polyphase induction motor. Okay, why polyphase? Polyphase because we are studying three-phase induction motor. Okay, so that's why polyphase induction motor is a single excited AC machine. That means only one supply is needed. Okay, so it is supplied power from a single AC source. It is a three-phase supply. So one power supply, which is a three-phase supply, is required to give the power to the polyphase induction motor. So it is a single excited machine. We in electrical we have a double excited machine also, that is beyond the scope of your syllabus. But for comparison with that, we are using this term single excited AC machine. So only one supply is required, and since it is three phase supply will be required. Water is two parts. One is the stator. So stator winding is connected directly to the AC source. So it consists of electromagnets. So we have to give supply to the winding so that has the electromagnets have their magnetic properties. And on the rotor side is are conductors which are placed in slots. So that rotor receives the energy from the stator by means of induction. So whatever you are learning in transformer, whatever you have learned in three phase, that all things come over here. So supply is three phase, working principle is based on transformer action. How the transformer operates, you have a supply to the primary, then a flux is produced in the primary, which gets linked in with the secondary. Then there in the secondary EMF is produced. Similar goes over here. When you give a supply to the stator, some current is flowing through the winding, then some flux will be produced, some EMF will be generated. That flux of the stator will be linked with the rotor, and in that magnetic field the rotor will start rotating. So only difference is that your transformer is a static device, there is no rotating part. In induction motor there is a rotating part called as rotor. Okay. Principal operation same. Now how can it be classified? According to supply you can classify it as two types. One is single phase induction motor, one is three phase induction motor. Our scope of study is only three phase induction motor. Okay. So next, according to construction, how can you classify? According to the rotor construction. Okay. So how the rotor is constructed, we can classify into two parts. It means two types. One is squirrel cage, one is slip ring. We'll have a classification of these two in today's lecture only. You will understand and have a look into how this looks like, how the rotor looks like. So this is what are the two classifications according to rotor construction. Almost 75 to 80% of the prime movers are induction motor, means whatever is driving, whichever is producing some mechanical energy, most of the applications we use induction motors. Okay, examples: fans, pumps, cranes. In fans we generally use single phase induction motor because in our home all supply are single phase, so all fans at our home are having single phase induction motor. In industries there are three phase induction motor. So basically what we have understood from here, the it has three, this induction motor has to be given supply of from a three phase. It has one static part known as stator, the rotating part known as rotor. It works on the principle of transformer action only, that is mutual induction. And water is two types according to the supply: single phase and three phase, and according to the rotor construction: squirrel cage and slip ring motor. Okay. So next is, I have tried to make a small comparison between transformer and induction motor. Okay. I've tried to make an animation over here. It's very small, just small animation. So what we have over here is a magnetic domain, which is common between the two. In a transformer and induction motor, we have both magnetic domain. Now, what is the supply in both cases? Both cases we are giving electrical domain as our supply. We are giving electrical energy as my supply. So energy input is in electrical quantity in both transformer and induction motor. Now if we take a case of transformer, so what will be the energy output? Okay. And what will be the energy output in case of induction motor? If I take a induction motor, what will be the energy output? Will be in mechanical domain, because what a motor does, it converts electrical energy to mechanical energy. So energy output will be in terms of mechanical domain over here. And this is what is induction motor. This is what, okay, I'll just change the animations. This is what is called the induction motor. Okay. And otherwise what can happen is, we can have a energy output in which domain? In electrical domain. At the output over here we can have output of electrical domain for a transformer. Okay. So in a transformer what happens, we are converting, I'll just correct it for now. We have a, so in a transformer what we are having electrical energy input as well as the electrical energy output. But for a induction motor, how will you compare? Electrical energy as my input and mechanical energy as my output. But the conversion of this from one input to another input is done through a magnetic domain only. So this is the common thing between induction motor and a transformer. So very important thing, you can have a just understanding about how transformer and your induction motor is related. Now let's go through some basic points over here. What are the advantages and why they are mainly used in most of the industrial applications? Generally, the constructions are very simple and very robust construction. So that is a squirrel cage type construction which we can use, which makes it extremely robust and very simple. We'll look into that also, why we are telling this point. Cost is low and very reliable. In case of induction motor, efficiency is very high and it works at a reasonably good power factor and requires minimum maintenance. What are the disadvantages? Its speed cannot be varied without sacrificing some of its efficiency. So efficiency will reduce slightly if you want a variation in speed. Obviously in any motors, if you increase the load, what will happen to the speed? It will decrease. So increase in load, decrease, there will be speed decrease, just as in case of DC shunt motor. And its starting torque is somewhat inferior to that of DC shunt motor. Compared to DC shunt motor, the torque is slightly less. So these are some of the advantages and disadvantages. You can go through it. But main thing is over here. So we'll look into the construction of the three-phase induction motor. First one is your static part, the stator. The outer part you are seeing, the outer part over here, this blue color, this is the protection given to the stator. This inner part, this one, follow my mouse, which is showing over here. This inner part is your stator. Okay. So in out we have to provide some protection because these are very high speed machines. If we don't provide any protection, it will come in contact with the outside area. and we have to perform many experiments with this. So we have to protect these windings from the outside contact. Means students are doing some experiment on this. If we leave this open, then it will be very dangerous to work. So we need to provide a protective covering, and also it will provide a support to the inner structure. So this blue color outside thing is called your yoke. Okay, yoke is generally provided for any transformer, which helps in means for induction motor, for any motor. You will see in the motor construction also there is a yoke outside covering. Okay, and these two are stands. On the stands they should be placed. They should be not kept with means this whole round structure, cylindrical structure should not be directly placed on ground. Why? Because if you placed on ground and this is a high speed rotating machine, your floor will crack. So it has to be present on some elevated position. So even though these stands are given, if you once if you look at any um, experimental setup, these are generally placed on some elevated concrete structure. Some concrete structure is made on the floor, and over that we place this entire structure. So that will provide enough protection for us, and also prevent the floor from cracking. So how are these coils made? So obviously there should be three coils over here. Okay, so three phases you are seeing. I can't say you how the coils are wound over here. These are slots over here. There are many coils which are present over here, but you can understand from here that three windings are coming out over here. Okay, three windings are coming out over here. What does this three windings signify? It is a three-phase motor. To one, it will be connected the first single phase, means A phase, to the another B phase, to the another C phase. So this is the three-phase stator winding. Okay, and this is winding. This is not a rotating part. It is just a structure in which only windings are placed in slots. So this is placed like this. So these windings are connected in either star or delta. I don't have to explain to you, because you know three-phase connection is possible in two types only, either star or delta. So these three windings which are placed in these slots over here are either connected in star or delta, but I can't visualize for you how the uh, connections are made within. So just for explanation, you should I have kept an overview of how the structure looks like. This is the stator part, and three terminals comes out. Okay, where the three-phase supply is given. So these three coils form three windings distributed over slots. These are all slots over here. So windings are placed, and three windings are brought out to give the three-phase supply. Now let's look into some of the important points. Um, So the stator of the induction motor is same as the stator of synchronous motor or generator. It is made up of stampings which are slotted to receive the windings. So don't have to go by all these meanings. Only thing you should understand, there are some slots present over here, and in the slots, these are all slots present. Okay, and in the slots, windings are placed. Now, stator carries three-phase winding and is fed from three-phase supply. Yes, because it is a three-phase induction motor, we need to have three-phase winding which has to be given three-phase supply. It was wound for definite number of poles, P is 2, 4, 6, 8, whatever may be. It depends, and number of poles will be affecting your speed also. We'll look into that, how pole and speed is dependent in later classes. So for just now, how we are, if we are wounding for 4 pole, we'll get a different speed. If we are wounding for 6 pole, we'll get a different speed. So that depends on how we wound the windings. Greater the number of poles, lesser the speed. So obviously you can understand these are inversely proportional. Later on we'll look into the formula. Okay, over here only it is given formula. Okay, just for your understanding, one thing again, all these things will be discussed in our next class. For today, since it is construction class and a basic principle of operation of induction motor, I just want to introduce to you something. Okay, next class we'll discuss all this in detail. So what I want to just bring into your note, that stator winding when supplied with three-phase current. So when you are giving the stator winding three-phase supply, okay, a rotating magnetic field is produced. Okay, the rotating magnetic, the field which is produced by this three-phase current or three-phase supply will be rotating in nature. That means what I'm trying to say is that if I have a B line like this, it will rotate in nature. Okay, it may rotate in clockwise, anti-clockwise, but it will rotate in nature. But in case of DC, what will happen? It will be fixed. Okay, since your magnitude is constant, but in AC, every time, at every instant, there is different values. Magnitudes of the voltages are different at every time, and those are phasors. You know your phasors. Once it will be directed at this direction, once it will be directed at 120-degree, others another will be directed at 240-degree difference. So all these phasor sum will give a resultant. So that resultant will be rotating in nature. So that's why I am telling that whenever you are using a three-phase supply, the field that is being produced is rotating in nature. This thing understanding we'll do in the next class. But for now, you just keep in mind that the field produced in three-phase induction motor is rotating in nature. And at what speed it is rotating? It is called as synchronous speed. Formula is Ns is equal to 120 F by P. So now you see this speed, N is speed, F is frequency, P is number of poles. So it is inversely proportional to your P. So as speed increases, pole will decrease. As pole increases, speed will decrease. That's why this point is required. Written. Definite number of poles will determine your requirement of speed. So that is why how your speed and pole is dependent. So for now, just keep in mind all these 4 points. This point we'll discuss in detail in our next lecture. Now going into the rotor construction. This is a stator part. Stator for anything, any induction motor, maybe it is a squirrel cage motor, maybe is a wound rotor motor. Stator part connections are fixed. Only difference we had seen is the rotor construction. So see the rotor construction over here. Okay, so these are copper bars, conductors. So this is looking like a cage, right? So this is a cage motor. It is looking like a cage. So this is a cage motor. So all these are conductors over here, which are closed, which are made short circuited at the end by end rings. These are called as end rings. End rings. Why I am making short circuit? Because then only current will flow. Otherwise there is no use, or there will be no load operation. No, if this is open circuit, where will be the current has the return path? So you have to make short circuit, and these two are called your end rings. So the copper conductors are placed in a cylindrical manner. This forms a cylinder like this, and with its end closed, short circuited by means of end rings, and so the structure looks like a cage. That's why it is called as a squirrel cage induction motor. Now on the right hand side in figure 4, I have shown you a schematic of a squirrel cage induction motor. This is how, if you get to see in a lab, or if you try to perform any experiment and buy a squirrel cage induction motor, you will get from the market this type of structure. Okay. And this one is called a shaft. This is called a shaft where the load is connected. To it, load is connected. So from here the load will be connected, and the load will be mechanically driven, because output of it is mechanical energy. So that means rotation. So it will be used for any application which is rotating in nature. So there you can use all these applications of here. Now a few small lines written for this. Almost 90% of the induction motors are squirrel cage. So all constructions made for induction motor are generally squirrel cage motors, because the rotor is a simple construction and most robust construction. Why I'm calling this robust, I'll tell you when I explain you your wound rotor motor. Why this is robust in comparison to the other one? Because all these are written in comparison to the next construction. Now the rotor consists of a cylindrical laminated core. Yes, it is. I told you it is cylindrical in nature. Okay, these are all laminated. Obviously, you know why laminations are required, because to reduce the magnetic core losses, the eddy current losses and all. And it consists of parallel slots carrying the rotor conductors. Okay, so all these parallel slots carrying rotor conductors or rotor bars, you can say. And not wires. These are bars of conductor. That's why I'm telling, these are not just simple wires. These are heavy bars of conductors made up of copper, aluminium, or any other alloys. Okay, and the next point very important is rotor bars are electrically welded or bolted into two heavy and stout short circuited end rings. So these two are end rings over here. So these are welded to the end rings to complete the entire connection over here. And it should be noted that the rotor bars are permanently short circuited over on themselves. So these are permanent. Your end rings are permanent over here. So you can't add any external resistance over here. So you can't add any external resistance, and thereby something will be affected due to this. Maybe the torque will be affected, maybe the speed will be affected. So there is no provision of adding anything over here. It is just one concrete structure. Nothing can be added. Directly from the shaft, load is connected. We can't control anything over here. So it is, that's why you can say it is robust. Okay. Now, if I add anything externally, maybe that external circuit may get damaged due to wear and tear. Okay. So that means we have to bring in construction and all to again to the circuit. Or if the external circuit is not working, then how can this induction motor operate? Then maybe it will not operate if the external circuit is not operating. But over here there is no external circuit required. We can't add anything. This is one complete structure over here. No addition external, direct load connected over here. Okay, so this itself becomes one complete structure, hence it is robust in construction. But you will see in the next motor which we'll discuss over here, which is the slip ring or wound rotor induction motor, and you will see that the construction over here is slightly different compared to that. So what it is? Now over here, you can see the wound rotor over here. So three windings, because obviously they will be either connected in star or delta. So it is connected in star. From the three windings, connection is taken out and connected to a slip ring and brush. Because why we are using this slip ring and brush? This slip ring and brush helps to make the rotor contact with your, just one second, just one. Okay, so what happens over here? We make this rotor being contacted with some external resistors. So that is made through your slip ring and brushes. Previously, had seen that this rotor was directly short circuited through the end rings. But now over here, we are trying to bring some control over here by adding some external resistors. So how those external resistors will be connected to motor? By some methods of slip ring and brushes. Okay, these are the three slip rings. These are the three slip rings. You can see these are the three slip rings. And this one is your shaft through which load is connected. Okay, we can connect in the external, three external resistance. See, variable. Obviously, variable resistance means we can bring about control by changing the resistance. What control you can bring about? You can change the speed. You can change the torque. We'll see how it is dependent on resistance. But for now, just understand what is the difference between the other thing. That was a complete construction over there. There was no external resistors could be added to bring a control over anything on in that rotor, in the type of induction motor. But in this case, we can connect external resistor, and with the variation in the external resistor, we can bring in some control over the torque and speed. Okay. Now, since these external resistors are connected, we have to bring in some maintenance of this external resistor. If there may be wear and tear of these brushes, so we have to go on maintenance of this. So it requires more maintenance than the previous one. And it is not a robust construction, because if there is any problem with the external circuit or brush, then we have to go for replacing it. But over there, no problem with that. That forms a complete circuit over there. So this is the main difference. The schematic, I have tried to uh, give you some pictures over here so that you can understand what are these two types. You can look into this. This is squirrel cage. This is your slip ring induction motor. These three are your slip rings. Now all these points, what I have discussed, all these points are written over here. You can go through it. By changing or by introduction of the additional resistance in the rotor circuit, we can change the torque and speed torque characteristics, we can bring about change. So we'll look into this later, but for now, just for an understanding, you should have a common understanding that why external resistance and why variable. Variable means that means we need to bring some control, and where we will bring the control in the torque speed characteristics. So all these few points are written over here, you can go through it. Now next slide, what I have done is try to give a small overview of what, try to compare your two, squirrel cage and induction wound rotor. I've almost explained all the points, so let's go through it. Simple and rugged, your squirrel cage. Wound rotor is needs slip rings, right? Or and brushes. So it requires some maintenance of the slip rings and brushes. So cost is less because no external structures are needed over here. Cost is obviously more. Copper loss will be small. What is copper loss? I square R. So if you are adding 3 external resistors, that will also contribute to the copper loss in the whole induction motor. So copper loss in this case is high. Efficiency obviously will be high because losses are less. Efficiency obviously will be low because losses are high. Starting torque is low in this case, in the first case, but with the addition of external resistance, we can increase the starting torque. How it is dependent, we will understand in our later classes. Starting current is large, starting current is low. Why low? Because we are adding external resistance, right? So total resistance of the circuit increases, so obviously starting current will be low. And speed control, there will be no possibility, but it is possible because we are adding external resistance. So from this point you can understand, just now I have told, so we can change in bring a change about in the torque and the speed with the use of external resistance. That's why, so you can control, so you can bring a control on the output torque and your speed. So that's why where you need to control speed and torque, you can use your um, wound rotor induction motor. Where you need almost a constant speed of operation, you should obviously go for your squirrel cage induction motor. Okay. Next thing, how the induction motor rotates. So we'll just have a small overview in next 3 slides. I have 3 more slides just for you. So we'll have a small overview on how the induction motor rotates, and next class we'll continue with all this understandings which we are having in a more broader way. Okay. So how a rotor rotates? Obviously some force will act on it, right? So that is given by your Lorentz force. Force is equal to BIL. Symbols have the usual meaning, all these are given over here. B is magnetic field, I is your current through the conductor, L is the length of the conductor. So suppose this blue lines which are drawn over here is your rotor, which is rotating in nature. So this is your omega. Let it be rotating in your anti-clockwise direction. It all depends upon your Fleming's left hand rule. So that is written in point number 3, which determines your direction of rotation. And let this B indicate your flux direction, flux density direction, or your field direction, whichever you want to say. Now, this field which we had discussed in a small point, we will take that point and keep that in mind and say that this field is also rotating in nature. So this field is also rotating, this conductor is also rotating. So there will always be a relative velocity between the two. So if it is rotating at A, this is rotating at B in the same direction, so relative velocity will be A minus B. So always there will be a relative velocity between your field and your rotor conductor. So that by Faraday's law, you can say because of that relative velocity V, you will get a EMF. E is equal to BLV. So the relative speed between field and conductors. Now, I'll keep a point in front of you today only. Next day we'll discuss in detail. But for now, if the relative speed becomes 0, so if B, this magnetic field and the rotor conductors rotate at the same velocity, so what will be relative speed? Will be 0. So EMF will be 0, there will be no current, I will be 0. If there is no I, there will be no force, hence the conductors will not rotate. So the rotor rotates in the direction of the magnetic field, but it tries to catch up with the magnetic field. It can't attain the same speed of the magnetic field, because if it attains the same speed of the magnetic field, then my relative speed between this magnetic field and this will become 0, and this EMF will become 0, and in turn, if there is no EMF, then how will current be produced? So my current will not be produced, I will be 0, so no force will act upon the conductor. So that's why your rotor, you may, when you'll be going to read some books or some in the notes which I'll give, you will see a point has been given that rotor speed tries to catch up with uh, the speed of this magnetic field, but never can be equal. This is the reason why it never can be equal. At what speed this B rotates, we had just discussed, just named it as ns, equal to 120 f by t. So this magnetic field rotates at some synchronous speed. This field, this conductors rotate at some speed in r. So speed of the rotor conductors. This is speed of the uh, stator field, that is given by ns. We'll go through this also in the later classes. So ns will be always greater than nr. Next, so this is how your induction motor rotates. So there should be a relative velocity between the two. So for that we'll get an EMF. For that EMF, your rotor is short circuited by means of end rings or through external resistors. So obviously there will be a current flowing. So if there is a current flowing, your force will be acting upon the conductor, which will make the rotor rotate. So this is the basic principle of how the induction motor rotates. So I have given a few this is my own explanation. This is the description which you may find in your books and wherever you want to study. So this is explained in a more broader way. I have explained in you a very simple way how it rotates. Now how the explanation has to be done, it is like this. When the three-phase stator windings are fed by three-phase supply, then a magnet, so you are giving the stator your three-phase supply. So a magnetic field is produced of constant amplitude but rotating at synchronous speed. So a B is set up, a magnetic field is set up which rotates at synchronous speed ns. Just now we have discussed. The flux passes through the air gap. So the flux passes through the air gap and sweeps past the rotor surface. So you can just look, this is your rotor. Okay, this is rotating in nature. Now this is a stator. Within this there will be the complete rotor structure placed. Now there should be a air gap between the two. When you are giving three-phase supply, some flux will be produced. That flux lines will pass through this rotor conductors also. So it will cut the rotor conductors. And there should be air gap, always gap between the two. Otherwise, how will this internal structure rotate? So there should be a gap also. So that is your air gap, which is called over here. So flux passes through the air gap, sweeps across the rotor surface and cuts the rotor conductors, which are stationary. At starting, your rotor will obviously not rotate, so it is stationary. Due to the relative speed between the rotating flux and the stationary conductor. So obviously you will get a relative speed. One is rotating at synchronous speed, the other one at the starting is static. So you will get a relative velocity, that is V. And EMF will be induced in the later. Obviously we have learned E is equal to BLV. If there is a relative speed, there will be EMF generated. So EMF is generated according to Faraday's law of electromagnetic induction. I'm not going into this point, we'll look into this point later. The frequency of the induced EMF is same as the supply frequency. Its magnitude is proportional to the relative velocity and its direction is given by Fleming's left hand. Now we'll discuss all this in the later classes. Now what happens next, what I told you, what will happen next? Since this rotor is closed circuit by means of end rings or by means of external resistors, now current will start flowing. So current is start flowing. Now if current starts flowing, obviously what will happen? A force will act upon the conductor and it will force this rotor to rotate. So it will force this rotor to rotate. You can go through this point. Okay. And rotor starts rotating in the same direction of that of flux and tries to catch up with the rotating flux. Again the point, tries to catch up. It can't never be with the same speed because otherwise relative velocity will be zero. So that's why this point is very important. It tries to catch up with the rotating flux. So this is a small description given over here which I have told in your words. This will be left handed. And at last, how the torque is produced. So this is very important. Obviously we have understood your torque, how the force is acting. So if force is there, torque will be there. We'll just look at a specific example over here. Less than a minute left. We'll continue after this only. Just 5 minutes discussion we'll have. So let the meeting end. We'll discuss in 5 minutes and end with that. Any doubt regarding this today's lecture what we had? This is just simple construction. You just need to just go through it. What is the difference you need to understand? If in a question this may ask you what is the difference between this, so you can go through this difference. And this operation is very important. How does in the induction motor rotate? This may come as a question. Okay. Rest all things are just diagrammatic explanation of how the construct. Okay. So here is the torque production. How will the rotor rotate in this direction is just given. You can go through it. So what is it stating? Figure 8a. This is your figure 8a. This shows the stator field which is assumed to be rotating clockwise, but ultimately the rotor will rotate in this direction only. So this direction is shown over here. What is the relative motion of the stator with respect to the rotor? The relative motion at the starting, it will try to oppose its motion. So its relative motion is shown in the opposite direction. So how will be the direction of flux due to the rotor current alone? It is shown in your figure B. It will be a dot. You just try to find out this. I'll keep a homework for you. Use your thumb rule. You know how to use your thumb rule and find out all this direction of flux. If it is a dot, in which direction will the flux move and all, you can find out. So I'm keeping a homework for you. Try whether these directions are same or not. Okay. And from that, after this, if you draw all this EMF and because of this current flow, you will see the rotor conductor will be rotating in this direction, which will be given by your Fleming's left hand rule. So this is how generally your torque production is done. Okay. So basically what is there? We have to give a supply, the same thing. We have to give a supply in the stator, a magnetic field, rotating magnetic field will be produced. In that, the stationary rotor will be placed. So since the rotor is stationary, there will be a relative speed between the two, ns minus 0. At the starting, the rotor is not rotating, so we'll get a v over here, we'll get a velocity over here, and that will, for that we'll get a emf. And because of that emf, because the rotors are short circuited, so there will be a current, and because of the current flowing, there will be a Lorentz force acting. So that will be a force acting. So a force will act upon the conductor, and this rotor conductors will start rotating, and slowly it will gain its speed and become close to my synchronous speed. But it can't be equal to synchronous speed, because if it becomes equal, the relative speed will be zero. So no emf, no current, no force on the conductor. So that's why the conductor that time will not rotate, and that's why we are saying that it tries to catch up with the rotating flux. The rotor speed tries to catch up with the rotating flux.